Hello, in this short video, I just want to go over an example and show you an alternative way to do a calculation. And what I'm referring to here is lecture number 6 or video number 6, example 1. And what we did in this example, we worked with coordinates. So I'm calling them y here. So we had coordinates y, which were x, y. And we had some coordinates r, phi, and we were working with polar coordinates. So that means we had x equals r cosine phi and y equals r sine phi. And what we did was I gave you the line element, the Euclidean line element, dx squared plus dy squared, and then we did a calculation which eventually gave us the line element in polar coordinates. And the way we did this was we took the definitions for x and y, we computed the differential, so dx, we applied the chain rule, so this was cos phi dr minus r sine phi d phi. We squared the quantity, we did the same with y, we put it all together, there were various cancellations, and we ended up with this line element. We can also write this, of course, using the definition of the metric. So if this is capital Y, then here we have Gij in the y coordinates, dyi, dyj, and here we have Gij in the x coordinates with dxi, dxy. And we know from the starting point that Gij in the y coordinates is 1, 0, 0, 1. And of course we know that Gij in the x coordinates is 1, 0, 0 r squared. However, there is a second way to arrive at exactly the same result, and that is using the definition of a tensor and its transformation properties. So if we use the definition of a tensor, so then we have that Gij in the x coordinates is given by the following expression. So you differentiate the y's with respect to the x's for each index that is available. So for a rank 2 tensor, these are 2 indices. And then you sum over the components mn in the coordinates x. To do this, we need the matrix of first derivatives of the coordinate transformations. So if we start computing the 1, 1 component, so y1 is x, x is r cos phi. If we differentiate this with respect to x1 is r, so we get dx dr, which is cos phi here. And then as we're staying in the first row, it is then dx d phi, which is minus r sine phi. For the second row, we are working with y. So dy dr gives us sine phi. And dy d phi gives us r cos phi. And I'm putting a little line in here just to separate this. And this is precisely the Jacobian matrix. And just for ease of notation, I'm just denoting this as JMI. This means if I want to find the metric tensor and the other coordinates, and if I want to use the very basic definition that this is rank 2 tensor, then I can just use this, put in the j's and see what happens. So for the first component, so G11 in the x coordinates, I get here the JM1, JN1, GMN in the x coordinates. So recall that this is the somewhat clumsy notation that we don't want to use. This is of course a y. And you see the notation is not nice because you have a combination of subscripts and superscripts, and the superscript gets put in a bracket so it doesn't get confused with the subscript, which is a real index. This is more of a label. Anyway, if we just do this for this example, it is just slightly clearer to write it like this. So here we have a summation over all possible index values m and n. So these are 4 terms, 1, 1, 1, 2, 2, 1, 2, 2. Looking at the components of G, the off-diagonal components are both 0, which means this sum, which contains 4 terms, will have 2 vanishing terms. So the 2 non-vanishing terms are J11, J11, G11. Why? Plus the term 2, 2. So 2, 1, 2, 1, G, 2, 2 in the y coordinates. We substitute in what this is. So J11 is cosine phi. So we get cosine squared phi. G11 is 1 plus J21, this is this guy here, is sine phi. Sine squared phi 1. So we get cos squared plus sine squared, which is 1. G12 in the x coordinates, which is of course the same as G21, is, so I'm working with 1, 2 now. So J M1, J N2, G M N Y. So as in the previous case, G only has 2 non-trivial components, the 1, 1 and the 2, 2 components. The other 2 parts of the sum don't contribute because G is 0. So we get here 1, 1, J 1, 2, G 1, 1 plus J 2, 1, J 2, 2, G 2, 2 also in the y coordinates. And this gives, so J11 is cosine phi, J12 minus r sine phi times 1 plus J21, which is sine phi, times J22 r cos phi times 1. And you see the terms are the same, but differ by a sign. Hence we get 0. And the last term is G22, so it's the same calculation again. JM2, JN2, GMNY. So again, these components are only 1. So we get 1, 2, 1, 2, 1 plus J2, 2, j, 2, 1, 1. And let's put this together. So j12 is minus r sine phi, but the term comes again. So this is squared plus j22 is r cos phi, and j, this is a 2 here, of course. Yeah, comes also squared. And so we end up with r squared sine squared plus r squared cos squared, which is r squared. Which means if we put all of this together, we can now write gij in the coordinates x as g11 is 1, g12 was 0, g21 is also 0, and here we get r squared. And this matches, of course, the previous result. So I thought that was a nice little addition to do this so that you can see that there are really two ways to compute this. I personally prefer working with these coordinate differentials here because I find them quite natural and I find this calculation very convenient. However, some of you might prefer working with the Jacobian and simply applying to the Jacobian to the relevant tensors that we are working with. It generally tends to be the metric tensor, which we consider under coordinate transformations. And once we've set the coordinates, we'll work with the metric tensor in this form. There's one little warning I would like to give you, and that is, do not be tempted to naively use matrix multiplication. So J looks like a matrix, and you know it's called the Jacobian matrix. So this is a matrix, and you can view it as a matrix. But don't use matrix multiplication here too quickly. Remember that an upper index corresponds to a column, and a lower index corresponds to a row. And matrix multiplication means that a column is applied to a row. But you see the G here has two lower indices. So that means that is more like two rows than a row and a column. So you can't really use the rules of matrix multiplication naively here. You have to be very careful. So the summation is in both cases over an upper index. So the upper index is a column. These guys down here are rows. So we are sort of doing something consistent because two rows apply to two columns, and then you get something out that makes sense. But be quite careful. So it's very tempting for students just to multiply J with G twice, and occasionally you get the right result, but that is mainly an accident. Most of the time you don't. So that's why I'm saying you can visualize rank 2 tensors as matrices, but you have to be incredibly careful to check that you are putting the correct things together. So here you indeed have two rows, but you can visualize it as a matrix, and this visualization seems to indicate that you have a row and a column. So you must distinguish between a tensor, rank 2 tensor visualized as a matrix, and something being an actual matrix. So the Jacobian in this form has a row and a column, and hence can be viewed as a matrix. This G can be visualized as a matrix, but it isn't actually a matrix. It's a rank 2 tensor and has very specific transformation properties, and this is what makes it a tensor. So I thought to show you this example just to make clear that this is a tensor, that these rules of transformations of tensors can be used explicitly, like in this example, or via the differentials more implicitly, because we change the coordinate differentials instead of the tensor directly. But of course you end up with the same result. So this video is a little addition to lecture 6, example 1.